Hello, hello, hello. Welcome to my latest live stream. I must apologize for that slightly delay with starting. LinkedIn doesn't seem to like live streaming. I'm having a few problems with it. And I have been all last week, so hopefully it's going to improve, but we'll see. It's quite a complex process trying to do live streaming, especially when you're trying to multi-stream across different platforms, such as I'm doing my YouTube channel as well, and also a bit of Facebook. See how we get on with that. So I must apologise, but everything seems to be working. If you'd like to type in the chat, let me know where you're watching from, and there we go. If it's all working for you, perfectly fine. If there's any issues, please comment below. Just be mindful, there is a bit of a delay between what I say and it coming out of your speakers. So when you type stuff to me, there's probably about a 30-second to a 60-second delay, depending on which platform you're using. So everything seems to be working. I think we've got some audio. Yes, we have. Okay. Right, so we're going to pick up where we left off last week, and we're going to continue talking through the Boeing Starliner propulsion anomalies incident that occurred. And we've made a lot of progress so far, but we've still got a long way to go through the investigation. Now, my ultimate intent from doing this case study is I want to sort of share, the learning and knowledge about STAMP, STPA, and CAST. And one of the ways I want to do that is through these live streams, but also I want to get together with everybody and have essentially a case study workshop where we get together on Zoom, live together, and we can then talk about this live, and you can talk about your experience and any questions that you've got, and we can learn about STAMP, STPA, and CAST through the lens of this case study. Now, this is the QR code. If you use your phone camera to go to this link, you can see I've written the link at the top, whiteley-safety.co.uk/PL. And there's a funky number there, 214-879-7358. That's just so that I can get you into my website working okay. And you'll go to this website, this web page, just stick your name and email address in there. You'll join a wait list. And then when the time is right, once I've finished doing the case study and I've put some slides together to explain some of the key points, then we can get together and have that live session on Zoom. So with that said, thank you for coming along. If you do have any questions, stick them in the chat and we'll get stuck in and we'll pick up where we left off. So where we got to last time was we started talking about the helium leak, section 4.6, analysis helium leak. We got quite far through that. Let's see how far we got. Yeah, we got to the end of that section. And so the next section we're working on is 4.7, analysis, deorbit capability, fault tolerance. So this is a slightly different topic. So let's take my jigsaw piece. I ought to make this available for download. I keep saying that and I've not done it yet. There we go. So it's excuse me, section 4.7. So let's start with that then. There we go. So make sure audio is working. Yeah, we've got some streaming. The internet's working. That's good. Okay, here we go. So following the first crew flight test launch, attempt, in conjunction with the discussions regarding leaks in the helium manifolds of the service module reaction control system propulsion system, NASA and Boeing teams, so let's just highlight them. So NASA and Boeing teams realized that the service module propulsion system was not two failures tolerant for the deorbit requirement. So I'm just going to make a note of that. It's not two failures tolerant for the deorbit requirement. Requirement 1130-80. So I imagine they've got a really elaborate requirements control system, requirements management system, and that'll be written in a lot of their safety case equivalent to safety case documents, and they'll use that as part of making go no go decisions. So of course, if they've realized that the service module propulsion system was not too failure tolerant before they did the actual second launch attempt, there's an interesting question there over, well, was it really appropriate to go ahead with the launch or not? And of course, we've just read the third sentence in a paragraph in a massive report. So of course, I'm anticipating there's going to be some more discussion about that. But from a safety constraints perspective, if that is the requirement, we need to be too fault tolerant for deorbit, and they know before they've launched that they're not going to achieve that. Is it really appropriate to then go ahead and risk doing that launch? Now, of course, I'm saying that from a position of not having read the rest of the report, so I don't know what I don't know. Maybe there's a lot of other things going on. So what I've said is a bit of a ridiculous lay thing to say, and I don't know that yet. I'm going to learn that as we go through the reports. But if that's the safety requirement, that's the intent, then it sort of raises eyebrows a little bit. Okay. And that is for an autonomous deorbit, by the way. So it is perhaps that they can still do a manual deorbit. So let's just underline that, autonomous deorbit. It may be that they can still do do a manual deorbit. It's just that that's not discussed at this point here. Right, so there are many cases where Starliner is too fault tolerant to deorbit burn. This realization was specific to the helium commodity within the service module reaction control system. To deorbit, the requirement is to be too fault tolerant for deorbit burn in all cases, meaning compliance to the fault tolerant requirement. It does not matter how likely it is to get into the failure case. The system is non-compliant even in low likelihood cases. After diligent review, it was determined that this shortcoming has been present in the vehicle design since the early stages of the design process. There have been... Hang on a minute. Shortcoming has been present in the vehicle design. There have been numerous reviews, boards, and discussions regarding deorbit fault tolerance across multiple organizations of NASA and within Boeing. Joint NASA-Boeing safety reviews, starting with Phase 1 in 2013. So I'm just highlighting yellow to remind myself that's a bit of time information that might be relevant. Included in the assessment of the service module propulsion system against fault tolerance requirements. Blankety blank did not support a too fault tolerant service module propulsion system in the Phase 1 level hazard report provided by Boeing and jointly reviewed with the NASA safety community. This flaw in the design was carried forward through all Starliner safety reviews leading to crew flight test. Okay, that's the Propulsion System Integrated System Review, August 21st, 2012. So that's quite a long time ago in the context of things. Had blankety blank and sufficient level of fault tolerant for the helium system in the dog houses. The propulsion schematic from the PDR in 2013 also has blankety blank. During this time, the planned deorbit configuration was communicated to be too fault tolerant and that only 6 RCS thrusters would be utilised for manoeuvres. Additionally, only 4 OMACs would be utilised at any one time. Below is the updated schematic and the proposed operating modes from the PDR. Which we can't see because it's blanked out, which is perfectly fine. I can understand they don't want to put a propulsion schematic in a publicly releasable document. I totally get that, you know. The propulsion schematic from CDR indicates 2 helium manifolds per doghouse and GNC subsystem CDR, which occurred in April of 2014. So that is guidance, navigation and control subsystem critical design review. So this is an important milestone in the program. Now indicates that the 4 OMAC configuration and 8 RCS jet config for deorbit fault tolerance. This design change between CDR, PDR and CDR is not flagged as an impact to the fault tolerance requirement for the deorbit. The oxidizer and fuel lines still meet the necessary requirement. It's only the helium used to pressurize tanks and pneumatically control valves that is affected. What? Okay, so yeah, okay, so let's keep moving on. This schematic is within the hazard report system blah, which included within the DPD 110 and therefore limited rights. So if I remember correctly, that's this type of hazard report, this document is subject to some kind of data protection contractual rights of release of data. Therefore, it can't be released in this report. And I wouldn't expect them to do anyway, to be honest. But if I've interpreted what this says so far, it sounds like the design was not too fault tolerant for the helium part of the system. And the helium part of the system controls the... where is it? Yeah, that bit there. It's used to pressurize... The helium system is used to pressurize tanks and pneumatically control valves. So we're talking about valve control. So if we get our little jigsaw piece out, everybody, we're talking about this control path here. So there's some actuators in there of which the helium system is contributing to, and the control of the helium system is in there somewhere. And that has an implication for thrust, controlling thrust. And it just, yeah. The shortcoming has been, after diligent review, it was determined that this shortcoming has been present in the vehicle design since the early stages of the design process. There's been loads of reviews, boards and discussions regarding that fault tolerance within Boeing and NASA. And then the safety reviews begin in 2013, include an assessment of that against fault tolerance requirements. Blankety blank did not support a 2 fault tolerant service module propulsion system in the Phase 1 level hazard reports provided by Boeing and jointly reviewed with the NASA community. This flaw in the design was carried through Starliner safety review phases leading to CFT. Now, this doesn't... I'm not quite sure I understand what's been said here. It kind of implies that the architecture, the design is a flawed design. It doesn't meet the requirement. So that's one thing. That's the first thing. But it seems to imply, and I might have interpreted it incorrectly, but it seems to imply that that wasn't obvious until there was a diligent review during the launch process. Or that's when questions were started. Or it seems to imply, that's one way of interpreting it, and I might be interpreting it wrong, so please, type in the comments, let me know what you think. But the other side of it is that they knew about the flaw in the design, in the requirements, not meeting requirements, and it was carried through all the way through to CFT. So this is kind of a second engineering topic that's been sort of found its way all the way through to the end. It should never have got this far. Or that's my interpretation. The intention is it should never have got this far. So why has it? And why has it been acceptable for the crewed flight test? Is it because there's so much pressure at that stage? Oh, well, we've got what we've got. We are where we are. I'm sure that's famous words that you've all heard. We are where we are, Simon, so we're going to have to do it. And I'm like, no. This is what the safety requirements say. If you're going to decide to violate the safety requirements the literal day before we're going to go flying, that's not really how the safety process is supposed to work. But if the safety engineers are overruled by project managers, then this is where we are. Right, so the propulsion system integrated review in 2012. So this is over 12 years before the flight, and had blankety-blank and sufficient level of fault tolerance for the helium system in the doghouses. So I'm anticipating that this blankety-blank, whatever this is, might be an independent safety system or safety function. That it doesn't matter really what the helium system does. We've got this blankety-blank. It does something that means we don't have to worry about it. Maybe I'm interpreting. I don't know what that is. The propulsion schematic from 2013, so a year later. During this time, the planned deorbit configuration was communicated to be too fault tolerant, but it wasn't. Is that what this is saying? Because if it was communicated to be too fault tolerant, let's look at our little jigsaw piece. If whoever this controller is, tells this other controller, hey, our helium system design is too fault tolerant, you could say that that's an unsafe contributory control action. There's a whole conversation there about, well, what do you mean by unsafe and what do you mean by contributory? Isn't it only known in the context of an outcome of an accident that, oh, well, actually, it should not have been communicated to be too fault tolerant? And only 6 thrusters would be utilised for manoeuvres. So again, if that number has changed over time, the architecture has changed, then that needs to be reconsidered. Additionally, only 4 OMACs would be utilised at any one time. So again, if that's an assumption that's changed, then the analysis needs to be updated. And then below is the updated schematic and proposed operating modes from PDR. So if that's PDR, so let's just PDR. There's my really bad handwriting. Let me try with my pen. So I've got one of these fancy pens. Let's see if it works. It's not quite as good as my Apple Pencil, but it works. It'll do. Oh, look, there we go. It's better today. Why is that easier? So that's the 2012 PDR schematic. So that's from up, well, it says 2013 there, but there we go. And then the propulsion schematic from the CDR, which we don't know when that was. Oh, there we go, April 2014, now indicates a 4 OMAC configuration and 8 RCS jets. So that's 6. This is 8. There we go. It's still 4 OMACs. So there's 4 there and 4 here. There we go. So it's got more thrusters. For deorbit fault tolerance, this design change between PDR and CDR is not flagged as an impact to the fault tolerance requirement for deorbit. The oxidizer and fuel lines still meet the necessary requirements. It's only the helium used to pressurize the tanks and pneumatically controlled valves that is affected. Okay, and then there's the propulsion schematic from 2013. So I'm presuming that's the CDR. Oh, what's this say? Yeah, yeah, okay. Let's keep reading. I'm jumping the gun. FMEAs and FMECAs. So FMEA is failure modes and effects analyses. And then FMECA is failure modes, effects, and criticality analysis. So these documents could be an update of these documents with criticality information, or they could be separate documents. And this says that it's so E14.04 failure modes and effects analysis, and then service module system level FMECAs. Delivered at CDR also indicate that the helium manifolds were reviewed during CDR. The FMECA for the blankety blank was evaluated for leakage. It was identified that leakage may result in the ability to control the vehicle during free flight, and did not list loss of crew, loss of vehicle as an end effect. Ooh. May result in an inability to control the vehicle during free flight, but did not. I mean, that is not good at all. That's really, really bad. So there's an immediate question there over the controller. Who does the FMEAs, the FMECAs? So that's the first question. The second question is who reviews them and signs them off? And then there's a third question for flight critical systems, and there's a little star attached to that. Is there an independent reviewer looking at this? Is there an independent forum that's looking at these and going, well, is this, does this correctly identify catastrophic outcomes? Yes, no. And has it set requirements for catastrophic outcomes? Yes or no? So there's sort of three little loops there to consider if we were doing the investigation of this, and also the process and the training for the individuals involved and the tool support, and then of course what is the context around these people doing this work? Is it a copy and paste FMEA from a previous incarnation of this design, or is it a fresh one? That needs to be considered. The OMAC blankety blank did list loss of thrust and loss of crew vehicle as an end effect, so it did do that. Okay, I mean that's good because that's what it's supposed to do, but the fact that this other one did not, that is a big alarm that should be going off in everyone's heads. That's not good at all. So let's just get my red pen out, everybody. Here we go. So FME severity classification. I believe, if I remember correctly, this is exactly the same issue that occurred with the 737 MAX accidents. The FMEA for the MCAS system did not adequately set the classification for severity. Okay. That's not good at all. Right, here we go. So this is a table, a row from the FMEA itself. And you'll notice this is the FMEA, not the FMECA. So there's two. One of them contains criticality, which is what should. And I am guessing, because some organisations, they use the label FMEA and FMECA, FMECA, to mean the same thing. And it could be that an FMEA in this context contains a criticality assessment. So they might use the term interchangeably. But these refer to two different things, by the way. This is a system level one. Now, the system level one might be an amalgamation or a summary of other more detailed failure modes and effects analysis. So it is entirely possible that somebody did a very detailed FMEA or an FMECA, and then the detail of that was not transposed correctly into the higher system level FMECA. And again, let's get our little jigsaw puzzle out again. It is really interactions between organisations and how they flow information to each other. In this case, it'll be in documents and tables, maybe databases, maybe tools. So if we're investigating that, they're the kind of things we'd want to understand and think about. But let's have a look at this then. So first off, when you're reviewing any FMEA, FMECA, one of the things I always do is I ask the question, where is the FMEA template from? Is it based on a particular standard or regulation, or if it's based on a company process, what is the origin and pedigree of that? If it's just copy and paste from the last the last project an engineer's worked on, or it's come from, copy and paste from off the internet. Maybe AI has said, hey, let's do an FMEA this way. I'm being facetious, but the point is you should have credible sources, credible pedigree for the processes and analysis that you use. So, of course, there are, in civil air transport, there is ARP 4761, Aerospace Recommended Practice, that has an appendix that shows how to do an FMEA. And I imagine that they will use something similar for this, but I don't. In fact, actually, there is a space standard one for this. It's called ECSS FMEA standard. There, but this is for the European for cooperation, so it's not for. Yeah, hang on there. It's in there somewhere. Standards, active standards. Let's search for FMEA. There we go. There it is. Look at that. So there is this one. This is the European one. So if you don't know about this existing, or if you do, I recommend having a quick flick through it. But of course, I'm allergic to FMEAs because I'm promoting STPA, stamp, and cast. But of course, I'm not suggesting you shouldn't do FMEAs. I think they still have a place. I still think they should be done, but they should be joined together with STPA, much like they are joined together with fault tree analysis. And we can have a conversation about that in the live session if you want to register. So there is a standard for doing FMEAs and FMECAs. There is a table in here somewhere, if I remember correctly. It's been a while since I looked at this. It's not that one. There we go. There's a nice table. Look at that. Right. So this is the European standard for doing space FMEAs. There's probably an American one, and they'll have used that. So just so you're aware. Right. No, that's not what we want. This one. So, actually, it's very similar. Very similar. Great. Anyway, so let's have a look. Item function identification nomenclature. Function isolates leakage. Okay. What leakage of what? Anyway, identification number. Let me zoom in for you. Service module propulsion dash HMI dash leak. Failure mode leakage causes. So there's 5 causes in there. Potential causes, mechanisms of failures, 15 of those. Sorry, there's 5 of those. Single point failure, yes, no. Interesting. I'd like some justification why they've said that. Why is it no? And again, this is just one thing. When you're doing any kind of safety case review, safety review, the question is, well, what is the claim? What is the argument? What is the evidence? If the claim is true or false, what's the argument? What's the evidence? Just saying yes or no is not. It's not adequate. And I could understand when you're doing an analysis like this with lots and lots of rows and tables, it may be that there's one or maybe let's say there's a subset of 5 reasons why it's okay or it's okay to continue when it's not. You could just put those in a table at the bottom and refer to which of those or which combination of those 5s are relevant. But it just would help to have an explanation for that. Design controls, mission phase, operational mode, entry, abort, local effects, next higher level effects, end effects. Okay, so this column is the column that doesn't have the judgment as to whether it affects crew safety or not. So this is where it should be in there. So what did they call it? Yeah, list loss of crew, loss of vehicle as an end effect. Did not list loss of, yeah, did list. Yeah, okay. So for whatever reason, they've not put it in there. So, the investigation needs to go and establish, well, why was that? And we're not here to point fingers and blame people. That is absolutely not what it's about. It's about understanding why does it make sense not to include that. And if it's literally, Simon, I'm using this really rubbish spreadsheet that does my absolute nutting and it's got 10,000 lines in it, a bit of copy and paste error is guaranteed. And if that's the case, and it is entirely possible, then the organisation needs to do something about that. And this is human machine interface. This is thinking about how humans do their work and how best to capture that work and make sure that it's error free. And that goes down to also about who does the review and in what form that review is done. And if you have a specialist AI for your team that could do this kind of cross check, that would be helpful. But of course, don't rely on the results. It's got to be a human that signs this off. Okay, so let's just zoom out a bit then. So this is the report for 1601. You notice there that number 1601. So I'm not sure if this is 1404. I don't know if they're the same thing. Oh, no. 1601's down here, isn't it? So I'm assuming that this report here is 1601, or is that supposed to be 1601? I don't know. I'll not use a red pen because that's a bit over the top, isn't it? There we go. Right. So the same failure modes, effects and criticality analyses were utilised during the Phase 2 safety review, which was... so that should be yellow to highlight a date. There we go, May 2017. So was this a Phase 1 review? I think I saw earlier on. There's an integrated system review there in 2012. It doesn't say that there was a phase... Oh, there we go. There's the Phase 1 review in 2013. So that's a Phase 1 safety review in 2013. And then the Phase 2 was in 2017. In fact, what I'll do is I'll use an arrow because it's a bit cleaner, isn't it, than some scribbles across the page. There we go. Right. And would be... So it's these same failure modes and effects and criticality analyses were utilised during the Phase 2 safety review in May 2017. So the first one was 2013. 4 years later is 2017. And would be utilised in developing and informing the relevant hazard reports. While it appears that many changes did occur when evaluating the Group 2 Service Module Propulsion FMECA 1601, so that's this one, just here, and HR 208, it still lists the end effects for blankety blank to be the inability to control the vehicle during free flight or for entry abort phases instead of loss of crew, loss of vehicle. So let's get a little jigsaw piece again, everyone. Let's just say, well, okay, so this is our FMEA analyst, and they've done their first order effect, local effects, next order effects, and they're writing in their FMEA report, what are the end effects? Well, the end effects is the inability to control vehicle during free flight. Now, it may be that it could be just finger trouble and they've accidentally deleted or not added the text they meant to. You know, we're all humans. But it could be they've made a conscious decision. Well, we know that there's an inability to control vehicle during free flight. Fantastic. But this individual at this level of abstraction in their team, you know, let's assume that this is an individual writing this and not a team with doing workshops. Maybe there is a workshop and they didn't have the right people in there. Or maybe the people reviewing these massive tables have just like got blinded to all the rows and they don't do FMEAs themselves. They just have to review them. They don't necessarily understand the implications. It's just they've missed it off. Or they're not able to assess whether it affects anything else, whether it will lead to a loss or not. Maybe they don't know that. Maybe they were supposed to update it and it's not been updated. Maybe they did update it, but Microsoft Excel, if it's an Excel spreadsheet, didn't save it, or maybe it got overwritten. There are many, many reasons that might explain it, both trivial and non-trivial. But what matters is this particular line was not lined up to those losses, consequences. But again, it depends how this analysis was then taken and used later on. We don't know the detail of that yet. But one of the other things I'm going to do is I'm just going to quickly go back over and just talk about this FMEA for a minute. Let's have a look. So this says isolates leakage is the function. It's the service module propulsion HMI leakage. Now it's not really clear to me what component this is relating to. Is it relating to the pipe work or the valves, or you know, the service module propulsion HMI leak? Is that what is HMI? Is that human machine interface? Is it helium mechanical interface? I don't know. It's not clear. But we know if we're thinking about things through the lens of STPA with this control loop, we're either talking about this control action, control path between the controller and its control process. In this case, the helium system is used to control valves. So we know that the component is inside this control actions control path here. We also know that there's some level of feedback involved in that in terms of the valve positions and whether the level of helium pressure and volume is reducing. So there is some level of feedback that's related to this. So we know that this line in the FMEA is directly relevant to these two elements of an STPA analysis, if that's what we were doing. So the first one, causes of a leakage, poor design. Okay, so if we're starting with, basics like that, this immediately turns people's brains off from a creativity perspective. What we should do is have an FMEA or any kind of safety analysis done in two parts. One is about the obvious, trivial stuff that everybody knows, and we don't need to. It needs writing down, of course, but it shouldn't be the main thing we're looking for, because these are the obvious things. It's like doing a spot the difference. Between a cartoon. There's two cartoons, and we're spotting the difference. These are kind of trivial things that we should certainly capture, but we're also, our creative brains are trying to find the subtle but non-trivial, significant things. And this approach just turns your brain off. I find it really undermines your creative thinking. It bores people to death. Anyway. Improper material selection. Oh, hang on a minute. Wasn't that a topic that was mentioned in the previous live stream about the interaction between nitrogen tetroxide, is it NTO, and the seals, the sealing rings, the O-rings? I wonder what the FMEA looks like for those O-rings, because that's not mentioned in the report earlier on. So maybe I'll make a note of that. Let's get my pen. Let's get on my high horse. There we go. What about? There we go. What about O-rings? NTO versus O-rings. FMEA. There we go. Assembly area and damage, over pressurization. Hang on a minute. Pardon me. Over pressurization. Improper handling. Why are they on the same line? Corrosion, contamination. They should be two separate things. Already, I'm not particularly impressed with this FMEA, but then I don't think I've ever read an FMEA that I've actually found quite good. I'll be honest. I'm not saying it's hard. I'm not saying it's easy, because it's not. It is hard. It can be soul destroying. So I totally understand. Improper design tolerances, improper material compatibility with hydrazine. So that was hydrazine there, look. But that's not quite the same as NTO, I don't believe. I don't know. Give me some abuse in the chat. Is hydrazine NTO, or I think there's some slight difference between the two. I don't know. I'm not an expert on this. Quality control failures resulting in assembly failure. I mean, again, failure. There might, you're losing when you just say failure all the time. Improper quality program to verify pressure band, improper cleanliness during assembly. You could say at the bottom of all of this, if you can read my handwriting, inadequate FMEA. There you go. Let's stick that. Copy and paste that 1,000 million times throughout all your FMEAs. There you go. That's value for money, isn't it? No, you see, the problem is this method, unlike STPA. I mean, there is an element of this in STPA, so it doesn't completely eliminate this. But one of the challenges with doing a table type analysis like this is you end up copying and pasting all of these generic scenarios. And don't get me wrong, some of them are very specific and very important, but a lot of them are quite generic. And it just turns the analyst's brain off. And then when you throw these documents at your group of subject matter experts that need to review this, when they're already very busy with their own stuff to deal with, you just turn people off. Your brain, oh God, this is just copy and paste. This is torture. So I'm not surprised, but I'm not impressed. I wouldn't give this. If I was asked to review this, I would be tearing holes through it. But again, there's a balance between tearing holes in an analysis that somebody who's completely disheartened and, soul is crushed, and then to say, oh, well, what you've done is a load of copy and paste nonsense. We're not going to accept that. That's not nice anyway. I've been on both ends of that, so yeah, I totally get that. But this is a bit superficial, and unfortunately, FMEA is a bit superficial. But it does have its place, in my personal professional opinion, when you have somebody who is an expert in the physics of failure of the things that we're talking about. So long as the FMEA is pitched at the right level of detail, where they can start adding, physics of failure. We were talking there about material compatibility with hydrazine. I would expect the person with the physics of failure and the knowledge of material compatibility to either be filling this in or providing the information to the person or team who fills this in, and that they've got a reference number and they can refer to a memo or some kind of technical report that says, yes, this is the material compatibility issue, so that it is traceable. Because a lot of these are just copy and paste. They might be just opinion, or they might literally be selected from a drop-down menu, copy and paste. And then the value of this method becomes, limited. Improper qual program to verify. Yeah, okay, so we've said all of this. Yeah. Not surprised. Talks a bit about pressure. Does it talk about temperatures? Is temperature involved in there? Pressurization, corrosion, improper design tolerances, compatibility. No, there's no temperature, temp-related stuff in there. Temperature, shock. Shock is a good one. FOD, or what do they call it? What's the term? Impact. Like if you're doing a particular risk analysis for a gas turbine jet engine that was to suffer an uncontained engine failure, and you've got bits of high energy debris flying around all over the place, you're thinking about the fuel manifold around the outside of the engine, for example, you'd certainly want to think about that. So you could have FOD, impact, high energy debris, micrometeoroids, I think was mentioned earlier on the other day, should I say. So let's stick micrometeoroids in there. Meteoroids. Is that right? Yeah, maybe. Okay, single point failure, don't know. I'm not so sure about that. Why? What's the justification? What's the reference for that justification? Because there should be, well, I say should, some organisations will have a failure modes and effects summary document which will essentially summarise all of these massive tables, and they will have a list of all those that are single point failure yes and then single point failure no, and then they will capture justification for those. So shouldn't normally be left just as a flat no. But yeah, okay. Design controls robust design, factor of safety. What factor of safety? What's the reference for that? What's the reference for that factor of safety? Is it 2 to 1? Is it 1.5? What is it? M&P approval, manufacturing and production approval. I don't know what that means. Maintenance, maybe. Inspection, workmanship, screens, quality acceptance, quality testings, and then inspection. Is that not the same as this? Design controls. Yeah, this is just weak. I've seen some pretty poor FMEAs in my time, and this is not giving me much confidence. Mission phase operational mode. So what relevance does that have? Is that when the leakage occurs, or what relevance does this have to the function or the failure mode? I mean, it may be there's another line immediately below this that talks about the other operational modes. one of the other things I'd look for is a reference for this mode. So is this a specific, defined mode phase that is used across all of the FMEAs across the entire system? Or is this just this analyst deciding, oh, well, it's during the entry and abort phase, isn't it, mate? Instead of, this is what we mean by entry and this is what we mean by abort. Because yeah, anyway. Local effects, first failure, none. Redundancy. I mean, are we talking about one bit of pipe or one valve that's leaking? Or are we talking about a complete loss across the entirety of the pipe work? Second failure, loss of propellant to thruster half system. So half system implies we've got a full system, which is two parts, and it's isolated and completely separate and cannot be, combined in a way that could lead to complete loss of propellant. And again, it says it says thruster. What about thrusters? Are there more than one thruster? Thrusters. More than one? Hang on. More than one. There we go. System. Third failure. Failed on excessively leaking thruster on remaining half system. Right, so let's get our little control loop out. Let's put it over. Let's bring it to the front so we can see it better. There we go. So the first failure, and we're talking about either the control path or feedback path. What is the first failure? So if we get failure mode leakage, if we get leakage, it's not clear what type of leakage we've got. Is there a leakage level below which we're not really too fussed about, and above which actually that's important, and then above that it's really important? And the reason I ask that is in submarines they have various standards that talk about leakage, water leakage, because of course you don't want to get water in the people tank, is the saying. Or if you do, you want to try and minimize how much water is in the people tank, because below a certain amount it's kind of normal. You're at sea, it's the Navy, you're going to get wet. You've got to accept that, because otherwise why would you join the Navy? But of course, when it's above a certain amount, then it can become quite important, and especially for controllability and survivability of the submarine. So of course you want to know what levels you're interested in, and generally there'll be some guidance or a standard for that. So I'm kind of surprised they've not sort of said, well, hang on, where's the pen? So 0 to 1 is complete and utter, everything escapes. But what is the spectrum of leakage in here? Is it kilograms per second, or is it tons or whatever it is? I don't know. Or liters. It won't be liters, will it? No, because that assumes a certain pressure. Anyway, so the first failure is, well, what do we mean by first failure? Is it that we affect the control path, or we affect the feedback path, or do we affect both of those? And then when we're talking about second failure, loss of propellant to thruster half system, is that one thruster or many thrusters? And is it on a particular side, or is it opposite sides, or what is it? Because that might be important. And of course, it's important to get your head around that this is a single, or we're saying helium leak, and we're thinking about, well, what is the single effect of that? What is the single second order effect? What is the single third order effect? There's no consideration in this analysis of what else might be going on, because there might be other things going on. We might have a faulty thruster, or we might have, maybe the branch that we maybe one of the two branches, I think it referred to branches. Yeah, maybe one half of the system is not available for some reason, a genuine reason. And we get this leakage on the other half. All of a sudden, it's a bit more serious than just this one single failure. And then the third failure, failed on excessively leaking thruster. So this is loss of propellant, and this is excessively on. So if you think about our control actions, I'll just jump up to the top to talk about types of control actions. Where's my little diagram? There we go, this one. So if we're thinking about types of control actions, not provided is effectively loss. So let's just get my pen. So not provided is similar to loss, or it is effectively the same as loss of whatever it is. And then provided is essentially a group of, well, these are all the ways that if it was provided might cause us a problem. And so we've got just a generic, it's just provided when we don't want it. That's sort of high level, a bit generic. But if we want to get specific, we have to explore, well, when we say provided, what do we actually mean by that? Is it related to magnitude, so in this direction, or is it related to timing? So, you know, if this is too early, say it's there, is that a problem? If it's supposed to be here and actually it's here, it's late, is that a problem? Or are we talking about the entirety of the duration of it? If it's too long or if it's too short, if that makes sense. And this is it really. So timing early, timing late, duration too short, too long. And then of course, if it's relevant, if you're talking about some kind of digital interactions, you could have the sequence elements to do with it. So normally it should be 1, 2, 3, but if you get 3, 1, 2, is that a problem? Or if you get 3, 2, 1, is that a problem? Because it may be that number 2 in the second position is treated as valid because that's how the system is designed. And then of course, if magnitude is relevant, you can think about too little or too much. So yeah, in terms of this particular part we're looking at, that we're zooming into, this one line here, this one line has 3 different scenarios in it, 3 different local effects. And this one here is excessively leaking, and this one is loss. So yeah, so we talked about that. And of course, this doesn't talk about the effects on the control system, the control loop, that this particular failure mode is relevant to. And that's where STPA comes in, because, well, both STPA and CAS, because they force you to consider, well, what is the impact of this helium leakage on my control actions? What is the impact upon my feedback? You know, is it such that, you know, a small leakage might lead to the controller using these systems to provide control actions? It might believe that something is safe when actually it's not. You know, so I'm hoping you can see that using STPA and using this jigsaw piece, it can really open up some really subtle but really, really significant non-trivial issues that may not be failures. Because of course FMEA is all about failures, and in this case not very good. You know, no disrespect to the people that have done this. I can completely understand. I've seen similar elsewhere. It's not, you know, I'm not sort of pointing fingers and saying, oh, everybody's bad. I'm just saying if you had a better tool, which is STPA, maybe using STPA in line with doing your FMEAs, you could do a much more cleaner job. And then next higher level effects, no propulsion flow to the thruster leg, lost of thruster leg, 1/2 system remains unless additional failures on second half system. So there's a big assumption there. So again, that is related to control actions, but possibly feedback. And then of course, end effects, inability to control vehicle during free flight. Of course, now if we were doing an STPA, we've already identified if we get this unsafe control action and it's due to issues with helium, we've already know within 10 seconds whether that's going to lead to a catastrophic outcome or not. And so you could cross-check with the FMEA and identify that weakness with the FMEA. Right, okay, so I've done that to death. I'm just going to have a quick drink. Let's just have a quick look at the chat, see if anyone is giving me any abuse in the chat. So let's have a look. I don't know if it's still working on LinkedIn. I think it is, but let's find out. YouTube is working. Fantastic. Hello, everyone on YouTube. And Facebook. Hello, everyone on Facebook. All 1,100 of my followers on there. It's fantastic. So that seems to be working. But LinkedIn, No, LinkedIn is live. Yes, LinkedIn is working. Fantastic. Wow, I'm amazed. Thanks, LinkedIn. It's not as if I don't pay you some money every month for you to work. Right. There we go. Okay, so that's still working. There's no comments. I've got a couple of people watching. Hello, viewers. Please comment below. Let me know you can hear me okay. And let me know where you're watching from. I'm always fascinated to know where people are watching from. And if you want to share whether you're watching it on a computer, or on a laptop, or your iPhone, or even a games console, I'd love to know. I had a friend, he passed away sadly a couple of years ago now, but he used to religiously watch me on his big TV with his PlayStation. So whenever I used to see in my YouTube stats that someone had watched on their games console, I was like, that's my friend Mark. Rest in peace, mate. Rest in peace. Right, let's have a drink now of talk. Excuse me. There we go. It's 6:10 already. Wow. Right, so let's look at this one. So this is FMICA report for Hazard Report 208, broken into two parts for readability. Because, of course, these spreadsheets can be massive. Right, so that's 208. Right, okay, so that is this one. So let's just highlight that. There we go. So this is 208. And this one was 1601. Pardon me. So 1601 is that one to there. There we go. And then for 208 is this one over here. So let's just drag this over here. There we go. That's it. Right. So let's have a look at this one then. So you'll notice we've got function isolates leakage. So that is the same. This one here is the same as this one. Again, I don't quite understand. And of course I've not been involved in the analysis, but I'm just, in terms of the function of the helium system that in this part of the spacecraft, my understanding its prime purpose is to support control of thrust. So why does this refer to isolating of leakage? Why is that? Why not control of thrust control? So I'm just going to make a note of that. Question mark. Thrust control. And I must apologise. Obviously, this session is supposed to be about STPA and CAST and stamp, and I'm here tearing through an FMEA. So, yeah. Anyway, let's keep going. So, SM prop HMI leak. SM prop HMI leak. So that is the same. Failure mode leakage. That is the same. Causes. Again, like I said, if you're doing tabular analysis like this, it is a good idea to have an index or a dictionary or a list of common causes so that you can use them across the entire analysis, and then have specific ones for specific analysis, specific rows, so that you have consistency across the document and you have traceability so that you can go back and trace it. So this might be reference materials, design, engineering, environment, manufacturing. Again, this is not enough. You know, what about micrometeorage? What about temperature? What about stress? What about the way the thing is installed? Is it tested before it leaves the factory? All of that good stuff. What about FOD? Cracks? You know, are there any cracks in the thing? Is it crack tested? Is it pressure tested? I don't know. This is just very, very weak. But I appreciate this is kind of common across a lot of industries, and I can understand why, but we really need to do better on this kind of stuff. And like I say, STPA allows us to be more laser focused than this copy and paste malarkey. Poor design, improper material selection, assembly area and damage. Overpressurization, improper handling, corrosion, contaminate. Yeah, so these are the same as before. As before. Single point failure, no, as before. Design controls, none. Entry abort, that's the same as before. Failure affects existing conditions. Okay, so local effects, next higher level effects, end effects. So that's the same. First failure, non-redundancy. Second failure, loss of propellant to thruster half system. Third failure, failed on excessively leaking thruster on remaining half system. Again, this is 3 different scenarios, and they should be explicit themselves, I think. So it's obvious that there are 3 scenarios here that we need to think about. I don't think this is good enough. If I was reviewing this professionally, I would be rejecting this with some big comments. And I can appreciate that some organisations might be like, oh, the information is there just because it's not in the format that you need. The information is there if you read it and you spend time reading it. Yeah, I get those comments, but come on, we should be trying to help each other here. This is a safety analysis. We should be taking it seriously and doing it carefully and diligently. And that's not a comment for the people that wrote this one. This is more of a comment for some of the people I've worked with in the past. And maybe I'll share that one day. Failure effects, no propulsion flow to thruster leg, loss of thruster leg, 1/2 system remains unless additional failures on second. So this is exactly the same as the other one. This is exactly the same as the other one. End effects, inability to control vehicle during free. Yeah, so exactly the same. When it says during free flight, just for a minute, just entertain me for a minute. Does this mean under crew control or automated control? And does it matter? Because free flight to me sounds like it's manual control of the crew. But does that imply that if it doesn't mention automated flight, then that's okay? I don't know. Failure mode detection method, blank. Oh right, hang on. It's blank. So that is, so they've chopped it out. They've omitted it. Okay, so let's go to our little jigsaw piece here then. So we have this problem in the control process, which is a helium leak. So what feedback do we get? What sensory feedback do we get? How do we detect it? Is it detectable? Who or what is the controller that detects it? What actions do they need to take? And of course, the big one is what is the time lag between detection and resolution? And is it so much time that actually it degrades so that it's unrecoverable, irrecoverable, and very dangerous? Is it even detectable? I don't know. These are all the questions that if you use a control loop to shape your to support your thinking, you'll be able to find things more detailed, more quickly. So there may be a detection method, and they've just not included it. But that's where we would think about, well, what is the detection method, and is it just feedback we're talking about, or is it actually we've detected it and we now can take some action, or we can't take action, but at least we know about it. So severity 4. So again, this stuff here, I would have a reference that says where this comes from. Where is this definition? It may be that in the header of this report it explains where all these definitions are, but it's always a good idea to remind everybody that these are based on specific definitions. They're not just made up on the day. Probability of occurrence, again, this is one of the reasons STPA and STAMP is the way it is. For complex systems, we often can't guess or have any data on probabilities. So why are we even wasting our time trying to put probabilities on things that's just, we're just bullshitting ourselves, excuse my French, potentially. Criticality is severity times occurrence, is that? So that's essentially risk in all but words. Oh, so it's a 20, everybody. Or it's a 4 times a 5. Ooh, is 5 high probability or low? Is it a scale of 0 to 5? Or is it 0 to 5? And if we have 5 by 5, it's 25 and we win a prize? I don't know. Is there a risk matrix that we're trying to work within the boundaries of? Are we trying to bullshit ourselves with a risk matrix? Critical safety item, criticality 256 or 56 or something. It says no. Why is it a no? Why? Why is it a no, everybody? Come on, what's the justification? Detection 4. Does that mean it's got a probability of detection of 4? And is that 4 out of 5 or is it good, bad? RPN, risk, RFN, severity, occurrence, detectability, whatever that number it is, 30. 80, sorry, not 30. Yeah, so my question is, well, once we've done all of this magical FMEA nonsense, no disrespect to the engineers, I'm critiquing the method and how it fits into the safety process. Once we've done all of these fancy numbers, and this is our FMEA process down here, where do these numbers go? And what do they actually do for decision making and beliefs of the controller for the team? And what actions do they take? Because we've said here, apparently it's detectable and it detects it with a number of 4. Great. Okay. What then? What does that do? What decision making does that number drive? And does it lead us to, oh, well, it has detection and it's perfect detection, so it's fantastic, let's keep going, let's move on, the design's fine? Or does it actually prompt a thorough engineering review? I don't know, maybe it's a rhetorical question. So yeah, that's fantastic. We've talked about FMEAs to death there. There we go. So we've got through 4.5 pages in an hour and 20 minutes, or an hour, should I say. Okay, so let's, we'll keep going to 4.71. Here we go. So redundancy to, hang on. Yeah, so that is a new page 94. So redundancy to combinations of service module propulsion system failures, including IPC failure. IPC, what's IPC, everybody? Where's the acronyms? This is a different acronym list. And it doesn't have IPC. Oh, it does have IP. Oh, Integrated Propulsion Controller. Okay, I've not heard that one. I don't recall hearing that one before. So maybe we talked about it the other day and I've completely forgotten because I've slept since then. Right, let's take that one and stick it down here. In fact, it's probably a candidate controller. So what we'll do... Oh, it's there, look. Integrated Propulsion Controller. We already had it. It was already on the radar, but I completely forgot. There we go. So integrated propulsion controller. So we could say, well, actually, Simon, this is the controller we're talking about. Maybe. So redundancy to combinations of service module propulsion system failures, including IPC failure. So integrated propulsion controller failure is addressed in Cause 8. Cause 8, Control 1, and Cause 9, Control 1 in the Hazard Report, November 2019. Cause 8 is failure to provide propulsive capability for attitude control authority. The relevance is that if blankety blankety blank were to fail leak, the vehicle would still have sufficient RCS thrusters to maintain attitude. What about changing attitude? Cause 8, Control 1 was closed with Monte Carlo analysis. Fantastic. And referenced the applicable VCNs. So they're the requirements, I think. pointing accuracy, pointing stability, attitude rate stability, pointing rate accuracy, and pointing rate stability. Okay, first point is this word here and here and here and there. Yeah, okay, so failure. I'm going to moan about this now, just bear with me a second. Let's write it on here in big words. Failure. Right. Most people will say that safety is about failure and success. So failure is bad, success is good. And what I'm here to say is that not all failures are bad or safety related, and not all success is good. It could also be bad if you have a success. And so the fact that all of this is about failure is great, but it misses out the what I call dangerous successes. So these are the situations where the system has behaved as designed, but it's dangerous and potentially kills people and destroys your mission, ruins your mission and everything else. And so if we're using failure-focused analyses and that's all we use, then we're going to miss these potentially dangerous success scenarios that lead to the same losses that the failures do. And so redundancy to combinations of service module propulsion system failures means that they're not also redundant to dangerous successes. This cause 8 is failure to provide propulsive capability for attitude control authority. Well, what if it provides propulsive capability for attitude control authority in a way that leads to hazards, losses, and accidents? And it's not due to failures. It's just, it does what it's supposed to do, and that leads to an accident. So this focus, I know this is the traditional focus of system safety. I totally get that. And we still need to look at it, but we also need to think about these other potentially dangerous successes. And that's what STPA is designed to deal with. The relevance is that if the blankety blank were to fail or leak, or dangerous success, everybody, the vehicle would still have RCS thrusters to maintain attitude. Great, that's a really nice claim. So let's do our safety case language. There's a nice claim here. There are sufficient RCS thrusters to maintain attitude control. Is maintaining attitude control the only thing you want, or do you want to be able to actually control attitude and move around and return the vehicle to Earth and all the other good stuff you might want to do? So that's the first thing. That's the claim. Let's have a reference to where that claim is actually. Sorry, it's off the edge of the screen, isn't it? Sorry, just bear with me a second. I'm there shouting and screaming. It's off the edge of the screen. You can't see it. There we go. So I wrote claim. So that's a nice claim. What's the origin of that claim? Where does it go? Where's it? What's its reference? Where is it actually captured? And it says that the cause 8 control 1, which I'm not really sure what that is. Is that in this? So is this cause 8, is it? So we don't know what the number is. So is this 8? I don't know. And it says there's a control. So there's some controls there. Robust design. Oh, right. Hang on then. So control number 1 and control. Oh, these cause 8 and cause 9. So they both have a control 1. So control 1 is presumably robust design, factor of safety. But is the design robust? How do you justify that? It's just words at this stage. It's just words at the moment. It's just words. It's just words. Was closed with a Monte Carlo analysis. Okay, well, why a Monte Carlo analysis? Why is that relevant? And I'm not being funny, but that's not really a technical analysis in the context of looking at the design of the components and the artifacts, as far as I understand. It's got some numbers in it, put a few numbers in there, fantastic. I'm not a big, I don't use Monte Carlo analysis, so I can't critique it or really talk about it. I just know enough that I know I don't know enough. There we go. Cause 9, failure to provide, again, there we go everyone, failure. This should be your new term when you go back to work tomorrow. If people start talking about failures, just remind them, what about dangerous successes? I've been listening to this bald bearded guy on the internet, and he's been banging on about these things called dangerous successes. What about those? Why don't we have a go with STPA? Let's have a go with that. Let's get Simon to come over and give us a hand. Right, so cause 9, failure to provide propulsive capability for translational maneuvers. So this bit is about attitude. Why don't I use my pen? This bit is about attitude control, and this bit is about translational maneuvers. So maybe that's why. Yeah, but you still need to be able to control your attitude, Simon. You can't just maintain it. At some point, you're going to have to change it, whether you want to or not. And Cause 9 Control 1 has nearly identical wording, but cites translational maneuvers instead of rotational capability. The verification of Cause 9 Control 1 is insufficient for closure and should not have simply referenced the redundancy in blah. The attachment 2 referenced in the hazard report does not list the associated burns for deorbit for 2 fault tolerance, as well as the GNC CDR documentation cited in the verification does not list out associated fault tolerance. The Starliner pit concurs with the STAR report that associated verification of this control was insufficient. Yeah, I kind of agree with that. Okay, but why? What was the organisation doing? Is it because they use an FMEA and it's a pain in the arse and it confused everybody and sucked everyone's life out of them and the will to live, and so they just wave stuff through? Or why was that? What was going on? The correct sufficient verification would have been the correct verification evidence for the VCN to verify and confirm sufficient two-fault tolerance, such as autonomous deorbit. So I was banging on earlier on about this definition of here. No. This here, free flight. Is it human or automation control? There we go. Apologies for the handwriting. Right, VCN CCT Rec 1130-80 autonomous deorbit RCTS 086 February 2021 is delivered and composed of math models and GNC guidance navigation control Monte Carlo runs blankety 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 blank was not considered. Doesn't sound very good. What is VCN? What is VCN, everybody? VCN, VCN, verification closure notice. Right, that's what that is. Right, okay. Let's go down here. Verification closure notice. Verification closure notice. VCN. There we go. Right, so I just get my little loop again. So these verification closure notices are apparently notices that float around the various systems between each other They'll probably be managed in some kind of formal method with a formal process. I'd be interested to know how and why that works and how that might contribute or undermine this activity. The blankety blank were never identified as a single fault. Oh gosh, wow. Never identified as a single fault that could lose two thruster branches, or whatever that is, blankety blank, were not explicitly included in the associated case matrix, despite multiple joint safety panels conducted by NASA with Boeing. A fundamental system level fault tolerance design flaw in the Starliner. I shouldn't laugh. The reason I'm laughing is because obviously in this case, with hindsight, it's obvious there's an issue. But the reason I'm laughing is if you used STPA, you'd have found this stuff. I'm willing to bet £1 million. If I had £1 million, I'd bet £1 million that you could find these issues up front without any of these, without all of this potential risk to life and cost and everything else. I absolutely guarantee you could find this kind of thing with that method, with this method, and I would be willing to help you to do that. It'd be like shooting fish in a barrel. I can't really talk about the European Space Agency stuff I've been doing, but yeah, anyway, they liked the results. And we're going to release some work on this, what we did with ESA in the future. But I can guarantee we could have nailed this with STPA. Call me on the bet, I guarantee it. That's a big balls promise in the marketing world. Anyway, the fault tolerance issue stems from the fundamental channelization design of the pressurant system. This basic flaw in the blankety blank of a major vehicle subsystem cannot be attributed to the lack of available data, given evidence this flaw was present throughout all phases of the safety review process. The flaw appears to be evident when reviewing the basic propulsion system schematics, including hazard reports, if reviewed at a higher level than component fault tolerance. As highlighted by the STAR report, the Boeing BO team. What is the Boeing BO team? Who are they? Boeing MO team identified the missing fault tolerance for deorbit capability and sent emails in 2016, 2017 and 2021. What? This is ridiculous. Like, seriously, what is going on? So if we're talking about the control loop, we've got these people called the Boeing MO BMO B-MO team, and they were sending messages. So if they were this organized, well, let's do it like this then. So let's bring that to the top. There we go. Right. Oh, where's it gone? It's disappeared. There we go. I'll bring that to the top. Bring that to the top. Bring this to the top. Right. Okay. So so if this was the Boeing MO team, and I'm assuming that they're atop of the, higher up in the organization, more authority, and they did some work, they received some information, did some work, and they said, hey, we've identified this missing fault tolerance for the deorbit capability. We've sent emails in 2016, 17, and 2021 to whoever this responsible party is. What happened with that? What was going on with that? The Starliner pit interviewed BMO regarding emails sent to engineering teams. So, engineering teams at Boeing. BMO personnel stated that there was a good relationship between the BMO and Boeing engineering. So, BMO, Boeing engineering. There we go. BMO personnel stated there was a good relationship. So I'll use my green pen. Look, everyone, I'm going to use my green pen for a change. Yay! There was a good relationship between BMO and BMO engineering, though the fault tolerance had been highlighted in multiple emails. However, There wasn't a push due to other work occurring which was given higher priority. Ooh. Okay. So these guys have been prioritized to work on other things. So who is that engineering team prioritizer? Who is that? Who or what is that? And how do they manage these issues in the issues list? That'd be interesting. There were numerous processes that should have caught this lack of fault tolerance. This represents a failure as part of the design phase. Yeah, I agree with that, yeah. That could have been caught in deliverables presented at CDR, Delta CDR, including the GNC deliverables and the fault tolerance verification products. This represents a process failure of the hazard report phase that has multiple review phases, tools, and individuals who are specialised in understanding fault tolerance, verifying associated hazard controls. This is also a process failure in the requirements closure phase and the associated delivery of understanding with what constitutes, sorry, you can't see that, sorry, what constitutes acceptable materials of closure of those requirements. Finally, this represents a failure in the operations phase with the lack of processes for capturing discrepancies, issues, concerns, or easily elevating critical items to both NASA and Boeing teams. Below represents a timeline of the different phases of the Starliner vehicle in which this failure mode was present and never addressed prior to the first launch of crew on Starliner. Okay, so the first thing I'm going to say about that is I'm not surprised at all. And that's not a criticism of them or the organisation or anything like that. It's just that this kind of nonsense happens in a lot of organisations. It is organisational dysfunction in combination with people trying to do the right thing, but then been overruled and other people making decisions and calling priorities that maybe shouldn't be involved in making these kind of priority calls. Or if they are, they need to document why they've made those decisions, but not lose these actions off the side of the list. These are things that must always stay on the work list, on the assumptions list. But this is, this is a challenge with any complex system organization. This is not, this is systems engineering is hard, and you have to be disciplined. And if you don't have processes that are working for you, or people that are, either not disciplined or not prioritized in the right way or given the support that they need, then we shouldn't be surprised this kind of nonsense happens. So obviously I'm very sorry this has happened, but I'm not surprised. I've seen this type of thing in more often than not, I would say, but that's because engineering is hard. Anyway, in fact, I need to make a note of that page. What page is that? Page 94. There we go. P94. Forward on to. Yes, there we go. That's a private note. Anyway, right, here we go. Design phase. So during the design phase, so this was 2015, 2014, 2014. Service module, propulsion abort, pressurization, FT variance. Is that fault tolerance variance. So this is 2015. Hazard report phase. So the NASA SRP, is that safety review panel maybe? I don't know. 2015, 2019. Requirements closure phase. So this is the particular risk analysis for loss of control, loss of maneuvering probably, I'm guessing. 2019. So that analysis is the analysis I would suggest should have captured, identified this and nailed this down and escalated it. So why didn't it? Autonomous deorbit requirement. So that came later. So it may be that it was okay back here, and then this new requirement came along and said, actually, we need an autonomous deorbit capability, which has certain fault tolerance requirements. And then that may not have been then fed back into all these documents and then updated and flowed through the process. I'm guessing. I don't know, obviously, but I imagine that's generally how you would do these kind of things. There we go. Right. Operations phase. So Boeing MO, whatever that is, I can't remember, flight controllers. So Boeing MO flight controllers. Let's just get this, put it over there. So Boeing MO flight controllers. Okay. Autonomous deorbit requirement. Yes, that's the same one, 2026. P. No. P for pen. So that is that one there. Boeing flight controllers, is that review, I think, during 26, 2017, 2021? There is no existing process for addressing... What? There's no existing process for addressing deficiency in design. What? Why? Why is there not? Why? I mean, that's... Why? That's pretty basic stuff. Why would it make sense not to have an existing process for addressing deficiency in design? Is it because it's too complicated to use, the system they've got, so it's been ignored or left off? If there is an existing process, it is insufficient, as evidenced by this lack of fault tolerance been identified for years after the design phase and not been sufficiently elevated, addressed. Spaceflight is challenging. Yes, I absolutely agree with that. Yeah, it is. But any kind of complex system engineering is challenging. So, it's not just that this application is difficult, the whole thing is difficult. These complex systems must allow for easy dissemination of information regarding failures which may endanger the crew or mission. The safe return of the crew is required to be too fault tolerant for entry, descent, and landing per CCTS requirement 1130. For the CST 100 service module to support too fault tolerant, there were 3 configurations available. OMAC configuration A, 1 aft OMAC pair, each of the 4 doghouses. OMAC configuration 2, 2 aft OMACs in each of the 2 opposing doghouses. RCS configuration 8 aft RCS jets. Due to blankety blank, it was discovered a single fault. Loss of top or bottom doghouse blankety blank results in loss of 2 of the above thruster configurations. A subsequent failure could result in loss of the remaining thruster configuration option necessary to safely deorbit. The primary cause for loss of a blankety blank within the doghouse are from a failed closed blankety blank. Could be failed closed, could be controlled closed, thinking about dangerous successors again. Or an unstable helium leak rate downstream of the blankety blank, resulting in the need to isolate an entire manifold. Wow. Okay. So, yeah, that's not good, is it, everybody? That's not good, viewers. Okay. Per PCB in 2024, CFT crew flight test P2D2 helium leak risk acceptance. Part 2 held on May 23rd, 2025. So this was after the launch, I think. The Spacecraft Systems Office requested approval of P2D2 flange leakage at 2x5 safety performance schedule risk for CFT only, with constraint to accept lack of fault tolerance at future PR. Yeah, you see, this is why talking about risks and acceptance of risks is a disaster, because the design is inadequate. You can't put a probability on it because it's inadequate. I mean, you can bullshit yourselves with some numbers and spend time making numbers up, but fundamentally, it doesn't address the fundamental design issues. This Poll approved the risk level as presented, but did not formally approve the lack of fault tolerance. What does that mean? What does it mean? Oh, well, we think we agree the risk is the same as presented, but we're not approving the lack of fault tolerance. The flight rationale supporting acceptance for the use as is approach to the helium leak in the P2D2 flange stood on the following. Leak was known to be located at the P2D2 flange per helium detection. So that's the sensory feedback that we don't know any details about because it doesn't mention it, around the port doghouse. Flight history showed no leaks greater than what was seen at P2D2 flange location. Conducted reassessment of seal characteristics, that was talked about the other day, determined applicability of 11 failure modes as face seals per the Parker Design Handbook. We talked about that the other day. Assessed common cause, determined this cannot be eliminated. Bounded operational aspects and margin, ability of the vehicle to tolerate 4 more P2D2 equivalent GHE leaks before management is required in a nominal mission. Analyze mission scenarios for manifold on time. Analyze worst case single leak with no O-ring resistance. Worst case stack of So I've been talking for ages and ages while muted. I've just realised, oh dearie me, that's not good. How did I manage that then? Did I mute myself? Was it an inadvertent mute? Did I mute and then not unmute? How long have I been going muted? That's ridiculous. What I'm going to have to do is just go back through the video and find out how long I've been muted. And then I'm going to have to either redo it or we'll have to move on and address it another day. But I'll just finish this section. Actually, what time is it? So we've been going 1:52:47. We just make a note of that. There we go. That's a bit frustrating. I'm very sorry, viewers. I bet you're screaming me in the comments, Simon, you're on mute. Well, maybe it's good because I've been saying lots of things, and maybe it's good not to share those. The flight, yeah. Anyway, given the analysis system showing robustness that could support feeding multiple helium leaks on the order of the P2D2 flange leak in concert, with high confidence in the helium isolation valves not failing closed, and options to manage leak rates by ground operations, the program board found a one fault tolerant propulsion system would be acceptable for a single flight. The 4 RCS deorbit option was stated in the front of the charts as not adding a level of fault tolerance and not being a certified capability. Additional discussion during topic D of the Delta Agency FRR for the SM propulsion system fault tolerance concluded with the following general agreement documented in the minutes as thruster burn contingency use would be used only for crew survival. A real-time IMMT, don't know what that is. Let's have a look. IMMT. There's an SMMT there, look, Starliner Mission Management Team. IMMT is not in there, so let's search IMMT. Oh, there it is. Look, ISS Program Management Team. There we go. Stick that in there. ISS Management Team would be used to determine the best course of action if failures put the vehicle into a zero fault tolerant case. It was confirmed that the crew could also be left on the station and returned home by other means as required. Unless, of course, the issues lead to the inability to dock with the space station. Or being able to transfer from the Starliner to the space station. I don't know if they can do in-flight untethered transfer. I don't know. Discovering the lack of fault tolerance for deorbit on the pad seems untenable. It doesn't seem untenable. It is. I mean, it's ridiculous. Considering this was the third flight of Starliner and the first flight of the crew on the Starliner, this could have resulted in a stand down to verifying the associated case matrices and similar analyses were valid. As detailed above, there were many areas in which this could have or should have been caught. However, the availability of operational controls to manage the helium system and the amount of commodity available on the vehicle created acceptable flight rationale to be considered. Utilizing ISS as a safe haven and the possibility of the 4 RCS deorbit burn as a last-ditch capability helped solidify that the risk was acceptable to proceed your launch. I mean, that's yeah, that's quite a brave thing to do, I think. Okay, so we made good progress there. I'm sorry that I was muted for quite a bit of that. I need to go back and figure out when I became muted and why I was muted. so I can do that. But anyway, for the next live stream tomorrow, same time, 5 p.m. BST, so UTC +1. I'll see you on the next live stream. Thank you very much for watching. See you soon. Take care.